Thank you for the organizers for the opportunity to speak. And I didn't dare to really use this smart board right here, so I made just simple notes. So another thing is what I want to talk about is just a model case of a discrete singular Radon transform, which is basically a discrete analog of a Hilbert transform along a cubic curve on a nilpotent group. So first, the general settings for this type of transformations. You have a discrete nilpotent group, and you can think of it as identified with just a d-dimensional lattice, but it has a nilpotent structure. In fact, any discrete co-compact subgroups of nilpotent Lie groups, actually one can introduce coordinates to have this setting. And then you have a polynomial mapping from Z to ZD. So basically you can think of polynomials with integral coefficients. It's a little less restrictive than that. And then you can form this operator T, which basically just you translate the curve, or in this case the sequence Pn, by the group multiplication to a point M, and along that curve you average this function. So as you see, it is indeed a discrete analog. Now this type of operators for in the continuous case, of course, were studied a lot. In the discrete case, such operators were studied when gamma is indeed a commutative lattice, and then very general results were obtained. In this case, this is the first attempt in joint work with Alexandru Ionescu, Steving, and Eli Stein to handle these operators along a curve. So it's so basically we so far just worked out a model case, and at the end I will talk about the more general type of operators, what should be done in order to extend these results. So in this model case, you just take basically almost like the simplest nilpotent group, the upper triangular matrices with integral entries, and a very simple polynomial sequence or curve on it, as you see, just the entries n and n square, and the result is that this operator is bounded on L2. Now, of course, it is not at all related to discrepancy, but I will make a little bit of effort to explain that in some sense the motivation, at least for me, behind studying this operator has to do something with the uniformity of distribution of points on measure spaces. So actually what I would have been, and we would have been happier to study, is the associated maximal, discrete maximal operator, which is written here, because proving boundedness in L2, or more generally in, let's say, LP spaces for such operators, maximal operators, is almost always implies a corresponding ergodic theorem. So what type of ergodic theorem one would get then? So imagine that you have a measure space, which is, I almost didn't put down, but it's the capital X is the measure space. And say you have a family of measure-preserving transformations on that. This family is T, and it consists of D measure-preserving transformation. And then say you have a polynomial map, Z to ZD, so the coordinates of this polynomial map are indeed polynomials P1 to PD. And then you can form a so-called polynomial sequence to every point on the measure space, which is a subset of the orbit of this point under these transformations, a very particular arithmetic subset. And basically, the corresponding ergodic theorem is just the analog of the ordinary ergodics, and when you replace the full orbit by just this sequence of points. So as you see, what we have here, oops, maybe I shouldn't. It's maybe better. This is the analog of the ordinary ergodic theorem over these subsequences. Now, if the transformation's commuting, then this result was proved in full generality by Bourgain, but the point here is if you just assume that the transformation generate a nilpotent group. And if you have, let's say, the right ergodic conditions on these family of transformations, which basically says that you don't have invariant sets, non-trivial sets of the measure space which are invariant under all these transformations, and neither invariant under their powers, then what you get from these ergodic theorems that the points are actually uniformly distributed. This sequence, this polynomial sequence of points gets uniformly distributed on the measure space. So that is the motivation for studying such operators. Just as an example, in that model case, what type of transformations generate nilpotent groups. So for example, if you take the two-dimensional torus and one transformation is just a shift in the first coordinate, but the other transformation is a shift in the second coordinate, but that depending on x. That's, for example, then those two transformations indeed generate the upper triangular 3×3 group of the upper triangular 3×3 integral matrices. And the kind of sequences, this is just an example of such a sequence of points. So, yes, as I said, the subject of this, I wouldn't say, I'm not really tried to ever major in history, but to me, the subject really started with the ergodic theorem of Bourgain, who handled completely the case of commuting transformations and arbitrary polynomials. So he proved the corresponding discrete maximal theorem and then the pointwise ergodic theorem. And actually, there was another really general and beautiful result due to Bergelson and Liebman, who handled the case when the transformation only generated a nilpotent group, but then only proved the so-called mean ergodic theorem, nothing pointwise. So that's the two main results. And what do I mean by the mean ergodic theorem? If you look at now, instead of the transformation on the space, you look at instead of the shifts on the space of functions, just the ordinary way. And you look at this, then you get sort of a sequence of operators on the Hilbert space. And this averages over these sequences converge in the Hilbert space at every function f. So this is the analog of basically the von Neumann ergodic theorem. If you would just put here n instead of p of n, you would get the classical mean ergodic theorem of von Neumann. And two remarks that this is the most general case. Such theorems can hold as if the transformation would generate an even larger group than even the L2 ergodic theorem does not hold. There are examples for that. And as I said, what we are interested is the pointwise result in the nilpotent setting. And actually, we have been working on this for a while and proved various results, but those results were always when you average or form singular operators on subsurfaces of relatively large dimension. Curves were always too singular for us to get a result. Yes. So, and going back to singular, discrete singular integrals, or this in the commutative case, surprisingly, that was settled quite later than the maximal theorem. Proving boundedness of such operators, I think, started with the work of Arkhipov and Askolkov, and that's roughly the same time Bergain proved in his maximal theorem, and then Stein-Wenger extended it, but the general result was just done by Ionescu and Wenger about, I think, 2005. So somehow the proofs doesn't follow from each other in an obvious way. So the second motivation is that such operators, of course, can be considered as discrete analogues of Hilbert transforms along curves on nilpotent groups, and then there was a lot of results. This motivation I mentioned because we use elements of some of the proofs in the continuous case, especially some arguments of Christ and then Ricci and Stein. So, a couple of remarks, a couple of key points of the proof. It's a little bit technical, so I don't want to get into it very deep. But first of all, so here is one argument in the continuous case, roughly speaking. Consider, for example, the same simple operator in the continuous case. So you take this TT square curve, you take it on the group of 3 by 3 upper triangular matrices with real entries and form the corresponding Hilbert transform. And one way to show, say, just the L2 boundedness of such operator is first just to decompose the simple kernel 1 over y into odd functions. Let's say psi of I, where psi of I is just the appropriate scale of an odd bump function supported near 1 and minus 1. So basically, if you decompose 1 over I, you decompose the operator into pieces. And these pieces satisfy, let's say, an almost orthogonality condition. That is, if you take two pieces, you take their product, it will have small norm from L2 to L2. And in the sense, it's actually exponentially small. It's bounded by 2 to the minus epsilon times the difference of the indices for some fixed epsilon, which doesn't really matter. So once one can prove this almost orthogonality, then one is basically done by the so-called Cutler-Stein lemma. So if the piece is orthogonal to each other, all of them obviously bounded. If you look at the definition, then the sum will be bounded on L2 as well. So, so that's one thing. So basically what will happen in the discrete case is that this won't be true, this almost orthogonality. But to find out a replacement condition, one needs to a little bit understand how this is proved, actually, this almost orthogonality in the continuous case. So I think this trick goes back to Michael Christ, that if you take the product of two pieces, then actually, if you just start squaring it and just neglecting a couple of terms, then actually you can estimate it from above by one of the operators times the other multiplied with its conjugate to a large power. And this is really nothing else than you know that L2 norm of an operator is the same as the square root of it itself times its adjoint. And if you repeat this and just delete a couple of terms in a clever way, you get this expression. Why this would be better than the original one? That's a question. Of course, you repeat it for a while, not forever, just something depending on the, say, the dimension, underlying dimension of the space. The main thing is that this expression, tj star tj to some large power r, will have a kernel. These are convolution operators on the group, whose kernel is basically something like the measure on the curve convolve with itself a large number of times. And then the basic principle is that one hopes that if you convolve this measure on a singular set a large number of times, you get a smooth kernel, or a kernel which has some little bit of smoothness. And indeed, this smoothness is expressed in this Hölder, I don't know how is it called, Hölder continuity type condition, so that, of course, they have some scale invariance. And so you think of here really that just j equal 1 and y magnitude is less than 1. And then if you integrate the difference of the kernel evaluated at the point x and for a fixed y at x dot y, then the integral of the difference will be actually small if y is small. Will be at least as small as y to some fixed power. In this case, actually, you can take, for example, epsilon equal 1 in this model case. That's also easy to see. And then the other thing is that these are odd functions, so their mean value is 0. So if you just look at now what is the kernel of the product of ti times this operator whose kernel we just described, it would be the convolution. This is a little bit stretching here. This is x dot y, where dot is the multiplication on the group. And then you can just squeeze in this term because the integral of psi I is 0. And then you can use these two conditions together to get almost orthogonality. So basically that's the idea of one of the idea of proving such theorems in the continuous case. So the main problem for us was, that's why we didn't really wanted to think about this approach for a while, that this is not true on the discrete case. The best we could prove, the best what is actually true for the norm of the product of two pieces, it is bounded by one term, which is what we need, plus another term, unfortunately, which is just basically as small, depending of the smallest of the indices. This is still the right estimate as long as I and j are of the same size, and we will exploit that. So at least in that case, we are fine. So the question is, of course, this condition as it is not enough to show that the sum of the pieces will be bounded. Oops, I think I already had that. So maybe since I'm kind of going quick here, maybe I could have put an extra sheet to explain this phenomenon a little bit further. So go back to the commutative case, take just Z as the group. That's commutative group, and then take just a very simple, take the curve or sequence n cube, set of cubes, and look at the Hilbert transform, discrete Hilbert transform among the set of cubes, and decompose it into pieces. So that's an analog of the operator we consider in the continuous case. So in this case, it is a multiplier. As it is a multiplier, and it's very easy to see what is the multiplier. It's an exponential sum. In the continuous case, it would be an oscillator integral. And that oscillator integral would be basically concentrated around 2 to the minus j. But these exponential sums not just concentrate in a small neighborhood of 0, but they concentrate in small neighborhood of rationals as well. So instead of in the continuous case, when the absolute value of theta is like 2 to the minus 3i, that's because of the cube, here, this operator, the multiplier won't get too small if it is this far from a rational point whose denominator is not too small. So if you multiply together two pieces, then you multiply together the multipliers, and then the L2 norm would be small if at every theta the product would be small, but that may not happen. Because they may align very badly. So maybe there are two rationals, such that theta is very close, but at the correct distance from them. And in that case, the product wouldn't be too small. It would be somewhat small because we have a little bit of cancellation near rationals. So the product would be about this small, product of the denominators to some negative powers. And that cannot be, that's at least as small as some negative, as at least 2 to the minus epsilon I, when I is the smaller index, because if you have these two conditions, then the two rationals has to be close to each other as well. But they cannot be really closer to each other than 1 over q times q prime, unless they are equal, which case you can handle separately. So at least you get this estimate, which is not good enough. But basically what happens that this phenomenon can very rarely happen. If you fix, say, Satan, you fix I, so you have one fixed rational here, and you look at the other j's, where this happens, those denominators are actually exponentially increasing, a lacunary sequence. So actually you get the same estimate if you multiply mi theta with the sum of all the other mj thetas, where j is bigger than I. You still get the same estimate as if you would just multiply it with 1. And that's the thing we want to exploit here. And then to exploit this thing, one has to look for some analog of the Cutler-Stein almost orthogonality principle. And, well, that's a bit different. So first of all, at least as long as you add pieces of the operators which are on the same scale, so between a number and a fixed multiple of them, for those pieces the Cutler-Stein lemma applies. So all these, if you basically chop up the total sum into dyadic pieces, then each piece is uniformly bounded, because for those pieces the Cutler-Stein lemma applies. So let's do that. So let's introduce these sums. Eta is some fixed number. You can think of 2, but the argument to work, actually it has to be just a tiny little bit bigger than 1. So then we know that these pieces are uniformly bounded. And basically then here is a lemma which wants to replace the Cutler-Stein argument. It's kind of, as I heard, it's kind of a bootstrap argument because it works. You cannot directly prove the quantities involved are bounded, but you can get a bunch of recursive relation between them, from which then it follows that they are bounded. Anyway, the replacement of the Cutler-Stein lemma is the following. So suppose we know the following. We have a fixed dyadic integer r and some fixed constants a and epsilon, such that the following holds. So we look at a number of these operators Sm, say they are going from m to k, m and k could be arbitrary positive integers. And then one thing is that we can't really prove that the sum is uniformly bounded from m to k, but we can prove that the large powers of them, you can think of them like self-adjoint, and then instead of this Sm star Sm, it is just powers of the operator. The sum of these fixed large powers of the operators, those are uniformly bounded. That's one condition. And the second condition, that there is some orthogonality here, that if you look at one operator and then you look at the sum of the others with larger indices, a large power of them, then the product, in the product you will have some gain. Okay, and all these estimates you assume are independent of k. So basically k is just kind of we fix k so that we don't have to write infinite sums here. They play a little bit more role than that. So if these two conditions, now what are these omegas here? These omegas are 0 or 1. So actually you need to set up the conditions that not just the full sum, but sub-sums are still fine. Then if you have this, then actually you can prove basically an induction going down that the sum of the operators are bounded. So this would be a replacement of the Cutler-Stein condition. Okay. So, and actually to be honest, because of this conjugate, you have to have some symmetric, very similar symmetric versions of this inequality. I just didn't want to write all 4 of them down. So anyway, so let's say if we can, this at least in the case, in the continuous case, this looks like true, but of course we cannot use multipliers because in the nilpotent setting these operators cannot be written that way. So let's, for simplicity, instead of these sums of these pieces, let's just look at large powers of the operators Tj itself. So these are convolution operators, and then we want to say a little bit mimic this second part of the argument that if you convolve a curve itself with a large number of times, it will be smooth. So what kind of problem, how would that show in the discrete case? So it is true that any power of this operator is a convolution operator with some kernel. If you it's not hard to calculate the kernel. So what would be the kernel of this operator? Well, it's basically you look at a point and you look at these discrete curves and you basically want to count how many ways you can get this point as a product of points from these curves. So, and then you can think of this psi j as weight functions, which basically restricts the argument to size of 2 to the j. So if you really look, what is this? The condition is a family of Diophantine equations because the multiplication is given in terms of polynomials. And basically what you see is roughly speaking, if let's say they would be positive, but the size of the arguments are 2 to the j. So in some sense, we're looking at the normalized number of solutions of a family of Diophantine equations. And our advantage is that we can choose this R as large as we want, so we can choose a lot of variables. And in this, I wrote down in our model case what are these equations. So remember that the polynomial curve was just n squared 0. Its inverse has a cubic term at the top. So if you multiply these matrices together, and L is a point in the group, so it has 3 entries, then the first equation is very simple. It's just the alternating sum of the coefficients equal L1. The second equation is quadratic. It's the alternating sum of the squares is L2. And the third equation is a little bit more convoluted because of the group multiplication kicks in. So it's not just an alternating sum of the q's, but you have all these mixed terms. So, okay, so what do we want? We want that we have, if we choose enough many variables, then we will have a very nice description of the sum, that is the number of solutions of these equations. And indeed, there is a beautiful theorem in number theory, goes back to Birch in 1965, which I didn't want to write down completely precisely, just essentially what does it mean. And what it means is the following. It's just first for one polynomial. If you have a homogeneous polynomial, P, in R variables, and you have some fixed number L, and you look at the number of solutions of the Diophantine equation such that P n1 to nr equal L, say that you fix the size of each coordinate to be some fixed size L. Now, Birch's theorem says that if in some sense, and what sense will be here, you have enough many independent variables, a large number of independent variables in this equation, or in other words, if the polynomial depends in an essential way on many variables, then there is a very precise asymptotic formula for the number of solutions. Now, what is this condition that the polynomial indeed depends on many variables essentially is given in terms of the variety where the gradient of the polynomial vanishes in C to the R. If the codimension of that is very large, with respect to the degree, I didn't want to really quantify that because in our case the degree of P is 3, then there is this, then one can write out a very precise asymptotic formula for the number of solutions. In our case, of course, the first So in our case, we have 3 polynomials. One is degree 1, one is degree 2, and one is degree 3. The first 2 are very simple. Each variable, it obviously depends on each variable in an essential way, because if you take the partial derivative of one of the variables, then it would be just in the first case 1. So for these 2 polynomials, of course, it's obvious that the gradient only vanishes at 0. The third one, which is a little bit more convoluted, it requires a little bit of work, but it's basically the dimension is 1. So for all of these polynomials, the codimension is at least 2r minus 1, which we can set up as large as we want if we take r large enough. So although the original theorem of Birch was for the number of solutions of equations, they work exactly the same way if you add up some weight functions over the solutions of this Diophantine equation, which is our case. And then if you basically follow his proof, which is kind of long, so I just want to a little bit try to describe the end result. What kind of representation do you get for the kernel in the discrete case of Tj star Tj to the r? So first of all, it will be a sum. And it will be a sum over rationals, which sort of reflects the fact that when we are on Z, and in that case, it's the inverse Fourier transform of the multiplier. And for the multiplier, we already seen that it's made of pieces around rationals. So if you take the inverse Fourier transform then of each piece, then you get certain terms. But if we take away the sum, then there will be one term which is independent of all these rationals. This maybe this one. And this plays sort of the essential role in the kernel. This is very, very close to the kernel, what you get in the continuous case. It's essentially, it's not exactly the same function, but it has exactly the same properties. And there is some error term in the kernel whose L1 norm is already exponentially small, so one can basically just neglect it. So that's basically where the proof starts, where one wants to exploit this. And basically also, this sum doesn't play that much role in the proof. It's a little bit, it's kind of not trivial, because you see this term is depending on L. But basically, you can make this term constant if you just restrict this operator instead of the whole Z3 instead of just a residue class mod Q, then this term becomes constant. So essentially, the operator becomes very similar to the continuous one. So basically, then one sort of tries to run the continuous theory to get this, to prove the boundedness. Now, in truth, you don't really. It's not enough to deal with a large power of one piece, but this some large power of sums of pieces. But there is this kind of fortunate situation that won't quite be it will be the number of solutions of the Diophantine equation, but not of a fixed size, but on some between L and some power of L. But if you choose this power very close to 1, then the whole asymptotic form, everything still works out. So basically, once you have these, asymptotic formula, then you can start work and prove these conditions of this bootstrap lemma or this substitute of the Cutler-Stein, and that's essential. That's very, very roughly how the proof works. Now, of course, this was just a model case, so finally I just wanted to make a remark that what chance would be, which I don't know, to prove this result in a general setting. So Of course, this looks kind of particular what we did so far. One thing which helps a little bit is that with standard or lifting arguments, one can reduce the case to a monomial mapping where each coordinates pj's are just powers of n and gamma to a free nilpotent group. But in that case, still, we couldn't, in general, establish this Birch's condition, although I think morally it must be true, but that's a different thing to believe something and to prove something. So even if I didn't hear 3 beeps, I would. I heard 2 now, but I stop anyway, so thank you for that. Yes? I can give you the... Yeah, for example, if you take just a line, but it's a nilpotent group.
So, but the line can be placed in the model that you have over there. If it is a line that is in the first, always tangent to the first layer of the certification of the algebra, or if it is not, does it matter at all?
Well, honestly, I didn't think about lines, but I think if I think what would happen if you multiply out, like instead of n squared, you have take n and n or something, or just n and 0, but then it would reduce to the commutative case. So if you take like something which doesn't reduce to the commutative case, like n and n, if you start multiplying, you still get, after multiplying a bunch of terms together, each coordinate an expression. Each 3 entry of the matrix would appear. And you would still, I think, would get the same phenomenon. So I think either it falls down to, say, a commutative case. So to some a whole thing is in some subgroup of the nilpotent group, in which case you just consider the subgroup. Or if it is not really contained in any subgroup, so if this curve generates in some sense the whole group, then the thing should work. Because I think that's probably one of the 2 possibilities.
From the point of view of the matrix, if you take something that is not in the first layer of the certification, even if it's not a line or something, then it looks like the absolute dimension is 2 instead of 1. It looks very fast. So it seems like the dimension is the wrong transform. If you're doing it with those curves rather than with the curves called horizontal curves. In fact, in the model that you have an horizontal curve. So I don't know how sensitive this magic is.
It's, for example, it doesn't really make difference if I put n squared 0 or n squared n cube for this method. It basically gives the same. If you take the inverse, it's already n squared n cube of Pn. So it's somehow, it doesn't matter. Yeah. I think he started.
Yeah, but
Yeah.
he can relate there is a relation between these things and Schrödinger equation.
Yes.
Maybe something like Schrödinger equation.
If I would know what exactly in this setting would be the interesting problem about Schrödinger equation, like on a nilpotent case or on more general groups, I don't really know. But that's maybe possible. I'm sorry. If P is not 2, yes, then it's much harder, which is seen that how much work Ionescu and Alexandru and Steve Wenger worked on it just to get on, say, Z for a polynomial curve, all P's. It's much harder. There is a higher notion of almost orthogonality. Almost orthogonality not in L2, but in L2K, which is much more arithmetic and much difficult, but basically that was their key observation to get it for large P's, for example, large exponents, the boundedness.